Okay, these are homework help problems for Chapter 4 homework. First, number 77, it says a 90-kilogram man and a 55-kilogram man have a tug of war. The 90-kilogram man pulls on the rope such that the 55-kilogram man accelerates at 0.025 meters per second squared. What force does the rope exert on the 90-kilogram man? Okay, so I'm going to draw a free body diagram for the 55-kilogram man. I can't draw a free body diagram for the system unless I'm looking at net force. So I have to look at each one of them individually. So I'm going to look at the 55-kilogram man since he's the one being accelerated. So what I can draw is a force that's being pulled on him, and that force is accelerating him at 0.025 meters per second squared. So I can use F equals ma. I know that the force of tension, I'll call this the force of tension pulling on him right there, is equal to his mass, 55 kilograms, times his acceleration, 0.025, in which case that gives me, this would be 1.375 newtons are pulling on him. And so it says, what force does the rope exert in the 90-kilogram man? Well, it's the same, because Newton's third law says for every force, or every action, there's an equal and opposite force. So whatever tension is being pulled on the 55-kilogram man, it's got to be the same that's pulling on the 90-kilogram man. So there would be the answer. The book gives us the answer as 1.4 newtons because technically, since 55 has two significant digits, we want to make sure our answer isn't more precise than our least precise measurement. So that's why they round to 1.4. Okay, next let's try 69. 69 says, assume that a scale is on an elevator on Earth. What force would the scale exert on a 53-kilogram person standing on it during the following situations? So we have the first situation being the elevator moves up at a constant speed. Okay, so if there's a constant speed, or if we're not moving at all, we have two forces acting on it. We've got weight pulling down, which is mg, and we've got the force of the scale, which is the same as the normal force, pushing upward. And if those two forces balance each other out, there's no change in motion, there's no acceleration, there's no net force. Okay, so that's for part A. Part A is forces are equal and opposite. There is no net force, therefore no net acceleration. Therefore, it's either going to be not moving or traveling up at a constant speed. Either one of those has no acceleration, constant speed, or no motion at all. But for part B, when it slows to 2 meters per second, now what's happening is, if it's moving upward and slowing at 2 meters per second, what that means is this force right here, the force from the scale, is not as big as the force that's pulling downward. So we have a net acceleration in this case, so we have a net force. And the net force is, I'll do the bigger one minus the smaller one, minus the force of the scale. Okay, so that is, the net force is mass times the acceleration. And I'll start plugging in values here as well. So we have the mass is 53 kilograms. And it asks for what force would the scale exert. So what we're looking for is that value right there. All right, and it gives us the, it slows down at 2 meters per second. So we're going to write -2 equals, now mass is 53 times gravity is -9.8 minus the force on the scale, which is what we're trying to find here, right there. This gives you -106. This gives you -413.4 minus the force from the scale. And if I add this to both sides, 413.4, I get, I'm sorry, this is not 413.4, this is 519.4. So you can add that to both sides. And that gives me the -413.4 equals, I'm sorry, positive equals negative force in the scale. And I should be more careful about my negative signs as well. This is the right answer, but here we have the net force, and I should not plug in negatives here because the net force is just, I'm looking at the magnitude of the net force is equal to the bigger one minus the smaller one. So this is correct right here. So I don't want to plug in more negatives, so I don't want to use that negative. This should have been a positive, and this should have been a positive. So when you subtract, then you get this positive answer. So when I write this equation, I'm already taking into account the positive and negatives here by using this formula that the weight minus this up here gives me the total net force. So that's the right answer, and that's in newtons, not pounds. We're using metric units here. And I think the book rounds this for sig figs, but it's approximately 413.4 newtons that will read on the scale. And that's for part B. We actually didn't do part A, but in part A they're just equal, so you just have the force in the scale equals mg for part A, in which case you just have to do 53 times 9.8, and that gives you your answer of 519.4. So that was the answer for part A. All right, let's move on to part C. Part C is actually the same. It says it speeds up at 2 meters per second while moving downwards. So basically, what that means is the weight is going to be bigger than the force in the scale, so that the net force equals mg minus the force in the scale. If it's got a net acceleration downward still of the same amount, nothing changes. Okay, so I would use this same equation, in which case you're going to get your same answer for the net force. So whatever answer we have for part B, that's the same as for part C. Part D, it moves downwards at a constant speed. Once again, if the speed's constant, direction doesn't matter. So this is going to be this equal and opposite. So you're going to get the same answer you got for part A. All right, part E, it slows to a stop when moving downwards with a constant acceleration. So it's moving downwards, but it's slowing to a stop. Well, if that's the case, then the force in the scale is bigger than the mass, so that the net force is going to be the force in the scale. The bigger one minus the smaller one. Okay? And they want to know what the force is. Well, all we can give is this, right? Because I'm sorry, they're asking for the force in the scale, so I'll do net force plus mg. I'll add mg to both sides. Would be the force in the scale. We don't know what the net force is. They don't tell us this acceleration. So it's mass times whatever acceleration is what we have here, which we don't know what it is. They say constant acceleration. So net force is mass times acceleration. So there would be my answer. You can factor out an m if you want. So acceleration plus g equals the force in the scale. So that would be our answer for part E. Okay, 82 is a tough one. They give us the weight of a plane. I don't know what catapult, I don't know what that means, but okay, so they give us the weight of some jet plane that's going to take off. And they give us the thrust from the engine, force of that, and it asks how much runway will it need to reach its maximum takeoff speed of 285 kilometers per hour. First of all, I'm going to convert this to meters per second. It's 285 kilometers per hour because we use meters per second. That's what we need. So let's multiply by 3,600 seconds in 1 hour all the way around. Goes on top. It's supposed to be a 3. And then let's get rid of the kilometers. We need meters, so 1 kilometer is equivalent to 1,000 meters. All right, this gives us approximately 79.16, repeating, meters per second. So we'll just say 79.2 meters per second. For our final velocity, that's the final velocity we want to reach, the end of this, in the horizontal direction. So let's use F equals ma now. We know the force from the jet. If we look at a free body diagram on this thing, we need to consider just the horizontal here. So we've got one force, and that's the force of thrust. That's going to propel this thing forward. And we know the force is, or that thrust, right down here, is 2.75 times 10 to the 6th newtons equals, the mass times the acceleration. So acceleration is what I want to figure out. I don't know the mass yet. Whoops, I'm sorry. It's 6.35 for the thrust. I don't know the mass yet, but I could find that because I know the force from weight. Weight is equal to mg. And they gave me the force for weight. They gave me that as 2.75 times 10 to the 6th. They didn't give me the mass. They gave me the weight. So I'll have to use that to find the mass. Divide both sides by 9.8. And I get the mass of this plane is about 28,000, I'm sorry. Yeah, 280,000 and 612.2 kilograms times the acceleration. There's F equals ma now, right here. If I divide both sides by that 280,612.2 kilograms, then I'll get my acceleration in meters per second squared, which is about 22.6 meters per second squared for my acceleration that this plane is able to accelerate at. I can use that with horizontal information because if I write down my x information, let me erase some of this. And if I write down my x information, I've got my initial velocity in the x is 0. My final velocity in the x needs to be 79.2 meters per second. My acceleration in the x is 22.6. My initial distance is 0. And the question they asked for is how much runway do I need? So what I'm looking for is my final distance. All right. So we've got an equation that relates to these two, actually. We've got this equation, final velocity squared equals initial velocity squared plus 2a bar change in distance. This is final velocity with average acceleration formula that we have from kinematics from Unit 1. We can use that here because we have all the information except for the change in distance, which is what we need. So we have 79.2 squared plus initial velocity is just 0. So that equals 2 times the acceleration, which is 22.6, times the change in distance. So we'll divide both sides by this number, by 2 times 22.6, whatever that is. And that gives us our answer, which is approximately 139 meters for our change in distance. So that's how much distance we're going to need. If we start from 0, we're going to need to go 139 meters in order to get that final speed according to this acceleration that we're able to reach. Okay, let's try another one. Let's say a girl and a boy are pulling on a rope, and there's no friction, so they're on ice basically. No friction at all from their feet. It says the acceleration of the girl is 3 meters per second squared. Find the magnitude of the acceleration of the boy towards the girl. Well, let's look at the girl since they gave us information. There's only one force pulling on the girl, and that's the tension from the rope. That's the rope, basically. All right, so we'll call that F sub t for force of tension. Now, that force has got to be equal to ma, according to Newton's second law. It's got to be equal to the mass of the girl times the acceleration of the girl. The mass of the girl is 45 kilograms. And the acceleration of the girl is 3 meters per second squared, so that's 135 newtons. So the force of tension is 135 newtons. Now, for every force there's an equal and opposite force, so if we look at the boy now, there's only one force pulling on the boy, and that's the same force. That's 135 newtons just going in the other direction. That's Newton's third law. So F equals ma for the boy now reveals that the force that's pulling on the boy is 135, the mass of the boy is 65. We can find his acceleration towards the girl. It should be less than her acceleration of 3. If we divide both sides by 65, we get 2.1-ish. So about 2.1 newtons for the meters per second squared for the acceleration of the boy. And that should be, since we called this positive in the beginning, this should actually be negative because it is in the opposite direction. So we should call that negative. Really, this force should have been negative here. It would have made the acceleration negative because this force is in the opposite direction. That's a little detail that we should pay attention to. But anyways, I hope this helps. We'll go over more questions in class.